Hi, pre-calc students. These are going to be your Trig Day 10 notes. So these are in your packet. If you want to open up your packet and find the title for Trig Day 10, we're going to get started by talking about some trig identities today. So we're moving away from equations just for a little bit. We will come back to them eventually, but we're going to start talking about some really important identities that are used later on in equations and in other contexts. And we'll start with identities that I think you're pretty familiar with. So the reciprocal identities are things like the fact that cosecant is 1 over sine. Okay, so just talking about the three reciprocal functions and defining those, the fancy name for these identities is they are the reciprocal identities. And then we would have that secant is 1 over cos. And then finally that cotangent is equal to 1 over tangent. So based on the way we're able to define those, what I want to do is just get a little bit of practice with the reciprocal identities. And we're given some information down here. In the first example, we're talking about an angle alpha, and it says identify the quadrant or quadrants for the angles satisfying the following conditions. So what we know about the first condition is that sine of alpha is greater than 0. Greater than 0 to you should be standing out as being positive, and secant of alpha is less than 0, which means that secant is negative. So all you're going to do is do all-star trig class and use the given information to determine what quadrant or quadrants, it could be more than one, where both of those things are true at once. Let's start with the first condition. If sine is positive, you're definitely in either 1 or 2, so you can cross off 3 and 4. But we also have to have true that secant is negative. So out of the remaining quadrants, is secant negative in both? Well, not quite. It's not negative in quadrant 1. Everything's positive there. So the only quadrant left standing is, in fact, quadrant 2. So that's the final answer for part A. That's literally all you're doing up top here is deciding what quadrant or quadrants would we be in. Next example is tangent is less than 0 and cotangent is less than 0. So if I start with all-star trig class, we know that tangent is negative and tan is negative in 2 and 4. And then the other piece of information is that cotangent is negative. Well, since cotangent is the reciprocal of tangent, it's negative in the same exact locations. So in this case, we have two answers. We have quadrant 2 and quadrant 4. That would satisfy both of those conditions at once. So in a lot of cases, you will just be left with one in the end. But since these were the reciprocals, and we're looking at where they're both negative, we get two possibilities there. All right, moving on to use a little bit more with some reciprocal identities. Use the identities to find the indicated function value. We're going to leave answers in simplest radical form. So all that means really is that we want to make sure we don't leave any radicals in the denominator. So for the first one, cotangent of alpha is what we're looking for. If cosine of alpha is negative radical 3 over 4, and alpha is in quadrant 2. So what we're going to have to do is sketch an angle in quadrant 2. Here's my little fishy alpha. Now, we've done this before where we label for cosine the adjacent and the hypotenuse. So for the given ratio and the given trig function, label the sides appropriately. So we've got negative radical 3 here, and we've got 4 there. All right, so then what we have to do is figure out what is cotangent of this angle alpha. Well, in general, cotangent of alpha would be the reciprocal of tan, which is adjacent over opposite. And if you look at this, I can see the adjacent is negative radical 3, but I don't have the opposite side to find. And boy, I really wish I knew how to find the other side in a right triangle when given two sides. Even though it's not a special length by any means, we have the skills to find this missing side, don't we? How are we going to do it? We're going to do Pythagorean theorem. A little a squared plus b squared equals c squared. So let's do negative radical 3 squared plus, I'll call this side b squared equals 4 squared. By the way, squaring this is always going to make it a positive, so don't make a little mistake there. But if 3 plus b squared equals 16, b squared would equal 13, and the square root of both sides would leave me with a radical 13 for that last missing side. Once you have that, adjacent over opposite would be negative radical 3 over radical 13. And in the last step, because we have a radical in the denominator, you're going to rationalize by multiplying the top and bottom by radical 13. And this is going to look a little bit odd, but 3 times 13 would be a 39 under the radical. And then radical 13 times radical 13 is 13. We can't simplify radical 39 any further. There's no perfect squares that go in. So this is the final answer in simplest radical form. I'm guessing it really is not the trig that's the toughest part about this one. It's maybe remembering a little bit of Pythagorean theorem, being careful with that, and then just remembering how to simplify and rationalize the denominator there. Part B is a really similar question, and I'll do it in the notes, but I would encourage you to hit pause at this point, see if you can do it on your own as well. All right, we want to find cosine of angle beta, and beta is in quadrant 3. All right, so here we are in quadrant 3. Here's angle beta. We know the ratio for cosecant, so cosecant, put that over 1 just to make your life a little bit easier so that we can label two sides. Cosecant we know is hypotenuse over opposite. So the hypotenuse is going to be 4, and the opposite's going to be -1. Now, I realize the negative's attached to the 4 up there, but remember, as kind of a general rule of thumb, you always label the hypotenuse as positive. I'm getting a phone call. Sit tight for 2 seconds. Mr. All. Hi. Yes. For the first quiz now, can I call you back when I'm done recording? I'm in the middle of a recording right now. But it's not a problem. I will call you back. All right, and I'm back. Okay, hopefully you fast forwarded through that part, and let's keep going. So if I find the missing side here, I'm going to need it, because what's cosine of beta? Cosine of beta is adjacent over hypotenuse. So the hypotenuse I know already is 4. What's the adjacent side? Well, if I call this a squared plus b squared equals c squared, just like we did up above. So a squared plus 1 equals 16. A squared is equal to 15 square root. This side is radical 15. Now keep in mind, because we're going to the left, we really should label that as a negative. Cosine is negative in quadrant 3. So as a final answer, negative radical 15 over 4. There's no simplifying to do there either. Right? We don't have to break down radical 15. No perfect squares. It's already in the numerator, so we're good to go there. All right, let's talk about some more identities. In the next example, we're going to bring back the good old unit circle to remember some good properties of identities here. In a unit circle, the radius is 1. Drop a segment down from this point right here, xy, to create a right triangle. We know that this is a length of x and that that's a height of y. If we do sine of theta would be y over 1, opposite over hypotenuse, which is y. Cosine theta, very similarly, is x over 1, which is x. So these are things we already knew, that sine of theta corresponds with the y value on the unit circle, cos theta corresponds with the x value. And therefore, tan theta would be y over x. But what do we want to build towards here? And we talked about this really briefly on the very first day of trig. If tan is y over x, we can express that as the ratio sine divided by cosine. And that will be an important substitution that we use later on. And we're gonna call that the quotient identity. We can express tangent as a quotient of two trig functions. So tan is gonna be sine over cos. That is kind of the main quotient identity. We can list another one here though, because we know that cotangent, which is the reciprocal of tan, would be the quotient cosine over sine, right? Just flip that over. So when we talk about cotangent specifically, we really list two things typically. If it's a quotient identity, it's cosine over sine. But if you go back to the first page when we called it a reciprocal identity, it's also equivalent to 1 over tan. And depending on what we're trying to accomplish, you know, the substitutions that we'll make for cotangent might depend on the scenario. All right, moving on from there. Now we're going to get into some Pythagorean identities. And you've guessed correctly here. If we're talking about Pythagorean identities, we're talking about Pythagorean theorem. If you look at this triangle up here, if I applied Pythagorean theorem right there, we would have something along the lines of x squared plus y squared or y squared plus x squared equals 1 squared. Hopefully that would make sense according to the sides in the triangle. And the only reason I'm writing y first is because then it's going to match really nicely with what I have written here already. But what is y? Y is really sine theta. What is x? X is really cosine theta. So if I replace y and x with sine theta and cosine theta, we get sine squared plus cosine squared equals 1 squared, which is 1. This is the main Pythagorean identity. I'm going to write down some alternate forms of this identity that I want you to recognize. Alternate forms would include if you get sine squared alone by subtracting cos squared to the other side, I'd want you to recognize that 1 minus cosine squared is the same thing as sine squared. Take some practice to get there, but this is something that I want you to be able to make a substitution directly for. 1 minus cosine squared is sine squared. Similarly, if you get cos squared alone by subtracting the sine squared to the other side, 1 minus sine squared is therefore cosine squared. So kind of look out for those situations. But there's actually 2 other Pythagorean identities that are derived from this first one right here. So in the next section, it says, if we divide both sides of equation 1 by sine squared, what would we get? Well, let's actually write that down. Sine squared over sine squared plus cosine squared over sine squared is equal to 1 over sine squared. All right, if I go through and do that, sine squared over sine squared is 1. Plus cosine over sine. Oh, wait, that sounds familiar from a moment ago. What was cosine over sine, that ratio? Cosine over sine is cotangent. So cos squared over sine squared is cotangent squared. Keep that squared. And then finally, 1 over sine, that's the reciprocal of cosecant. And there's kind of a fun phrase that us math teachers love to use to remember this identity, and it's 1 cot is cozy. So if you remember 1 cot is cozy, that's going to help you to remember that 1 plus cotangent squared is cosecant squared. All right, finally, the last Pythagorean identity comes from taking the one at the top, sine squared plus cosine squared equals 1. But instead of dividing by sine squared, we're going to divide everything by cosine squared. There we go. All right, so when I do that, sine over cos is, sine over cos is tan. So sine squared over cosine squared is tangent squared plus cosine squared over cosine squared is 1. And then we got to remember that that 1 over cos is the reciprocal of secant, so therefore that is secant squared. Of course, we have a fun phrase to remember this one. Tanning once is a secret, or 1 tan is a secret. And I have a good story for you next time I see you in class about that. Okay, so tanning once is a secret is the good way to remember that. By the way, the first one, do I have a good one to remember this? I don't know. Sometimes students say like sines cost $1. Sine squared plus cosine squared equals 1. If that's a good way to remember any of these identities, go for it. But we're going to need to know these for sure. These are going to be great substitutions that we're going to use in some identity proofs. And that's what we're going to finish today's lesson with. If you go to the next page, which says verifying identities, you verified identities probably for the first time in Algebra 2. And the difference between an identity and an equation is that an equation is only sometimes true. For example, 2x equals 6, it's only true when x equals 3. Whereas an identity, no matter what you plug in for x on either side, this one is always a true statement. Yeah, x plus x, that's always going to be 2x, and that's exactly what's on the other side. So what we're going to do to prove identities that it contains some trig functions, we're going to follow these tips over here. So step number 1, look for ones and or squared terms. It could be one of those Pythagorean identities that we just saw. So if you see sine squared plus cosine squared, you're going to replace that with 1. But also look out for this. If you see 1 minus cosine squared, that's going to be sine squared. So you can make some replacements based on the Pythagorean identities that we just talked about. All right, step 2, write in terms of sine and cos. So that's usually a good hint. Every single trig function can be written in terms of sines and cosines using the reciprocal identities and those quotient identities, right? If you have tan, that's sine over cos. If you have cotangent, cos over sine. So maybe it's a good idea to make everything in terms of sines and cosines to be able to simplify. And then finally, do some algebra. You might have to do some factoring. You might have to add or subtract fractions. So there's going to be some algebraic situations that come up that we have to resolve. And then hopefully the goal in the end is to make the two sides look equal. Now, when you're working through an identity, this first example here, I'll tell you, you want to kind of draw a wall where the equal sign is. You can't cross over one side to the other because this equal sign is kind of like a big question mark right now. We have not proven that these two things are equal yet. So I can't add something to both sides. We can't multiply both sides by the same amount. I'm going to jump right into example 1, and I'm going to make it look real easy for you. When you see trig functions squared, especially being added or subtracted, I want you to think Pythagorean identities. Sines cost $1. Sine squared plus cosine squared equals 1. That is the very first identity. I don't want to say it's the most important one, guys, but it might be. This one comes up all the time, and it's alternate forms as well. So if you know that sines cost $1, sine squared plus cosine squared is 1, on the left side, change that to 1 over sine x. Oh, and by the way, what is 1 divided by sine x? It's the same thing as cosecant of x. That's exactly what we have on the other side. So within your identity proofs, you can work down both sides if you need to, but you can't cross over. You can't say, oh, I'll multiply both sides by sine x. Don't cross the wall there. But I've just proven that these two things are, in fact, equal to each other by using some Pythagorean identities there. Okay. Here's what I'm going to do in the next example. In the next one, we have a little bit more complicated. Tangent of beta times cosecant squared of beta, and then 1 plus tan squared on the bottom. I want to prove in the end that this equals cotangent of beta. So I'm going to leave cotangent alone. That looks pretty simple as it is to start. But one quick way to start something like example 2 is let's make a substitution right away in the denominator. 1 tan is a secret. I don't want people to know I go tanning. So therefore, this is equal to secant squared down in the bottom. Let's do that first. Tan beta times cosecant squared. I'm going to change the denominator into secant squared. That is a legal move. Check it out. 1 plus tan squared is secant squared. So we just made that substitution right there. All right. What I'm going to do next is now I'm going to do the trick in the second step here. Write everything in terms of sines and cosines. So we have to now remember some reciprocal identities, and then tangent is a quotient identity. It would look like the following. Tan is sine over cos. So that's the first change I'm going to make. Times cosecant squared would be 1 over sine squared. Just make sure that when you change a squared term that you change it to a squared quantity if you're going to find that reciprocal there. Okay. Secant squared on the bottom is 1 over cosine squared. So that's what we have now. I'm going to kind of clean this up a little bit by saying this sign would cancel with one of the signs down here. When you're multiplying fractions, you can do some cross canceling. So that leaves me with 1 over, multiply the denominators, cos beta, sine beta. And then the bottom is 1 over cos squared beta. There's going to be kind of one final step that I use here to clean up this complex fraction. Complex fractions, we usually think of multiplying the top and bottom by an LCD. But if you just have a single fraction over another single fraction, you can fix that by multiplying by the reciprocal of the bottom. Here we go. Okay. This is a legal move. I'm multiplying the top and the bottom by the same thing. So that's like multiplying the overall fraction by 1. The cos squareds would cancel. Great. What's going to happen up on the top? Well, on the top, this cos would cancel with one of those coses. So when I think about what's left over, you're going to multiply the tops and multiply the bottoms. What is that equal to? Cosine beta over sine beta. Now, all along the way, I want you to think, what am I actually trying to prove this crazy mess equals? I'm trying to prove it equals cotangent. Is cosine over sine equal to cotangent? Sure is. It's a quotient identity. Check it, put a heart, a smiley face, whatever you want. When I get down to that last step, cosine over sine is in fact cotangent, and that's exactly what I have on the other side. It takes some practice to get used to how to solve and how to prove trig identities. But we really have to be very comfortable with the identities. If you're a flashcard person, this is your unit. You're going to need to know all these identities. So at the drop of a hat, you can make these substitutions and then do some algebra to simplify there. I will save example 3 for class. So we'll do that one, and then we'll do a little bit of practice probably from the homework too to get you guys going. But that's it for today. Hopefully we'll do pretty good to remember these identities. Some you already knew, some we're going to take a little bit longer to learn. If you have any questions, certainly let me know.